A QR code sticker gets scraped against the edge of a table, losing an entire corner. Yet your phone still scans it successfully with a quick sweep of the camera. The first reaction feels almost strange, because any document that loses 30% of its content usually becomes useless. In the QR world, however, that level of damage is closer to a minor stumble in the data. The error correction system inside the matrix works like a reconstruction team, automatically filling in gaps you cannot even see. What makes this remarkable is not just the high fault tolerance, it opens the door to thinking of QR as a kind of living code that can evolve over time. And from there, a new question emerges. If everything had a QR code, how differently would the world map operate? The foundation that allows QR codes to survive physical damage lies in the Reed-Solomon error correction levels. This algorithm is designed to rebuild information even when part of the data is lost due to scratches, dust, or distortion. When the camera scans the code, the system does not attempt to read only perfectly intact squares. Instead, it samples data regions and uses reserved redundancy to reconstruct the full bit sequence. At its highest correction level, a QR code can recover from damage affecting up to 30% of its surface area, comparable to tearing away nearly 1/3 of a sheet of paper, while keeping the message readable. It sounds almost extraordinary, but it is simply the result of intentionally storing additional backup data, evenly distributed across the matrix. This distribution resembles information transmission models in space communication simulations, where data is spread out to minimize the risk of total loss. QR codes apply that principle at an everyday scale. Because of this recovery capability, codes printed on shipping boxes, utility poles, or curved surfaces continue functioning after days of exposure to rain and sunlight. Data durability becomes the key factor that makes QR practical in real-world conditions, where contact and dust are constant. From that mathematical foundation, the idea of the immortal QR began circulating among users. Now imagine every object carrying a QR code. That would mean layering a second informational surface over the physical world. Every wall, every shirt, every tree could contain a gateway to expanded data. A shirt might link to its manufacturing history in Bangladesh, the amount of water consumed during dyeing, and its shipping journey through multiple ports. A tree in a park could reveal its species, age, health condition, and conservation plan. If implemented nationally, such a system would create a scannable world map, where raising your phone would unlock hidden informational layers. Versions of this idea have already appeared in art exhibitions and smart city projects, where each object can open a narrative accompanied by scientific data. Expanded further, it could reshape education and tourism. Children might scan geological samples to instantly learn their composition. Travelers could access the history of buildings while walking through old streets. Even healthcare systems could attach QR codes to equipment for maintenance tracking. As augmented reality technology matures, these codes might disappear from plain sight, but remain visible through camera lenses, a world full of information waiting to be unlocked. One of the most intriguing developments is the concept of dynamic QR codes. Traditionally, people assume a printed code is fixed forever. With dynamic QR technology, the visible grid remains unchanged, but the underlying link can be updated continuously through a server system. A single poster can update event details without reprinting. A store can change prices in real time without replacing stickers. Movie tickets can automatically deactivate minutes after scanning to prevent fraud. The image stays static, but the data flows behind it. This capability has become essential in QR-based payment systems in many countries, where displayed codes refresh constantly to prevent duplication. When you combine strong error correction with dynamic linking, you get a system that is both physically resilient and digitally flexible. This combination makes QR codes one of the most versatile encoding systems in use today. They do not require high resolution to be read. They tolerate dirt, tears, and curvature. They can change content without changing form. Together with the processing speed of modern cameras, these features create a technological symbol with a lifespan far longer than many predicted. Every time you scan one, you activate a data network that appears almost self-operating. Looking at the QR structure again, you see a technology that balances simplicity and sophistication. It is nothing more than black and white squares. Yet it withstands damage like a deep space communication system and updates like a live website. All of that is packaged into a small square, often stuck slightly crooked on the edge of a table. If you enjoy dissecting the hidden logic inside everyday objects like this, stay tuned for the next episode, where we explore how a simple plastic bottle cap uses material mechanics to contain internal pressure without needing thick threads. The closer we examine familiar objects, the more we realize they are far from simple.